tray. Number what? 20. 20. Oh, it's right there. Was there a particular part? Both A and B, or? The general gist, I'll just say this, and then you can tell me if there's like a specific part. The general gist with log equations, if not every term has a log. And so on both A and B, there's a term after the equal sign without a log. It doesn't matter where the term is, but as long as not every term has a log, the general idea is collect all the terms with a log on one side so that you can condense them down to one log. So that's what I did on both of them. Condensed using the product rule here and quotient rule here. And then once you do that, you can rewrite it using around the world. Rewrite it as an exponent. 3 to the power of 1 is equal to the argument. 10 to the power of 1 is equal to the argument. And then whatever kind of equation you get from there you solve. Marcus. Oh. Yeah, actually, Momo pointed that out to me. Miraculously, this plus sign changed to a minus sign, which that was incorrect. That was my bad. Plus, plus, plus. So that would be positive. And then it doesn't look extraneous anymore. So I should check my answers, huh? Looks like positive 1/3. Was that your question? Okay. Any other questions? Ooh, sweet. Well, we are going back to the world of reality checks again. And remember, this really is actually better than what I was doing the first unit, because I still will not enter in reality check grades until I grade the unit test. So if the average is lower than your unit test, they just won't go in. It'll be your unit test. But if it happens to be higher, it can only help your grade, but it can't hurt. So, just try to remember that and stay loose and stay comfortable. I'm going to pause the video. Questions? So just remember, it's just like taking the derivative of a natural log, except you're going to throw in the natural log of the base. So 1 over the argument times the derivative of the argument, but just also divide by the natural log of the base. And then same thing here. 1 over the argument times the derivative of the argument, but divide by the natural log of the base. So any questions just getting to this point? And then, because of the way the multiple choice answers were given, you had to combine it into a single fraction. So you had to find that LCD. So any questions getting down to the answer? Anybody one more time looking at it? Alrighty, there's number 2. Everybody's so quiet. I don't know how to read this. Any questions about number 2? We're ready for number 3? Number 3, right there. Number 3 was a little tricky. It's just weird. But again, general rule of thumb, when you have something to a power, you don't know what else to try use substitution. Also, if you got a composition of functions, try use substitution. So, yes? The numerator in parentheses?
Should be in parentheses.
The numerator is all one single thing. It's just 7 to the power of negative x to the 10th. So,
because it might look like negative 7, so that's all about.
Well, even if it was written as negative 7, it's the same thing. Because remember, there's a difference between that and this. So, yeah, either way, I don't need parentheses. Good point, though. Any other questions? All right. Well, then let's do this thing. Let's talk about some inverse trig. Let's take a break from this long stuff. All right. I think I closed it. Don't look! Woo! The secret! Just kidding. All right, some inverse trig. But first, before we get into inverse trig, and that's cut off. Can I move this? I don't know if I can move this. Ah, I can't. There we go. So there's the title, Inverse Trig, and today we're going to talk about differentiation. And then the only thing left in this unit is to do inverse trig integration. And we'll spend a couple of days on that. The second day will really be a focus on just integration in general. But today is differentiation. But before we do that, let's just remind ourselves about something from pre-calc. How to do something like this problem. How do we do something like this problem? Well, do what, Yoj? Draw a triangle, exactly. Remember, anytime that you see inverse trig, think of it as the angle. So this part right here, think of it as the angle whose tangent is -3/5. So if we draw a triangle with one of the acute angles having a tangent of -3/5, this problem actually turns into a fairly easy problem. The only other thing that we do have to be careful is when we got the numbers like this, we got to be careful about the quadrant that we draw it in. So the range for arctan, where do I want to put this? Range for arctan. Does anybody remember what the range is? Rena? Oh, you have just made your integrated math 3 STEM teacher extremely proud. Yes. It is -pi/2 to pi/2. And if we go back to our days of the unit circle, it's been a long time since we've looked, I don't know what's going on there. Since we've looked at the unit circle, -pi/2 would be down here. Sorry about that. And +pi/2 would be up there. So if we start from -pi/2 and go to pi/2, as far as the unit circle is concerned, the range for arctan is in quadrants 1 and 4. In quadrant 1, tangent is positive, and in quadrant 4, tangent is negative. So when we draw this angle, or this triangle with an angle whose tangent is -3/5, we're going to go to quadrant 4. So this whole thing is just to tell us which quadrant to draw it in. So I shall now draw a triangle in quadrant 4. Oops. Quadrant 4. So any questions why I'm picking quadrant 4? Now, I need to define one of these angles. So I am actually going to say let theta equal arctan of -3/5. So I know what I'm dealing with. And where do I have to label theta on this triangle? Any ideas? Or does it matter? I don't know. Rena? So in corner number 1 or corner number 2? Yes. And I should have done that. So yep. Always label your angles have to be from the origin. You're going to measure to the x-axis by the origin, always. So now that we got that, I can rewrite this problem So my original problem was the secant of arctan of negative 3/5. But just above, I have stated that theta will be arctan of negative 3/5. So this is really just whatever the secant of theta is. And now I have a triangle that I can easily answer what the secant of theta is. In terms of opposite, adjacent, and hypotenuse, anybody remember what the ratio is for secant? What's on top? Number one? Oh, hypotenuse. Okay, you got that. And then what's on the bottom? All right, hypotenuse over adjacent. So I'm going to go ahead and label my picture here. If theta is the angle whose tangent is negative 3/5, then opposite over adjacent has to be negative 3/5. Now just be careful about that negative. Opposite over adjacent has to be negative 3/5. But looking at the coordinates, only one of those can be negative. Is it the 3 or the 5 that's negative? Yeah, I see people showing me on their fingers. The 3, because it's on the negative part of the x-axis. So we got that. Oh, wait, we don't have the hypotenuse. And you guys said I need to put the hypotenuse on the top. How do I find the hypotenuse? If only we had a theorem to find the third side of a right triangle. Yeah, the Pythagorean theorem. Now, and if you can do this in your head, Pythagorean theorem is one of those things you don't have to show your work at this level. 25 plus 9 is 34. It'd be the square root of 34. Does anybody need me to work that out, though, to see where that came from? Okay. But then we got it. So secant of theta is going to be the hypotenuse over the adjacent. The hypotenuse is root 34. The adjacent is 5. And that's it. We're done. So there's not much work to do. This work right here can be more in your head. But this is kind of explaining where all the blue work is coming from. But if it helps to write all this out, feel free. But the blue work is all you need to show. And there's just not much work. Yay! So any questions about that? Because I have a couple for you to try. Now, before I set you guys loose, let me just say this real quick. Because I know, like, especially my students that I had last year in STEM, I don't know if you remember for number 2, we did there was a lot we went into of you had to be careful which quadrant you're in, and sometimes there's 2 answers, and it became kind of messy. We're not going to go down that road right now. So for number 2, because there's nothing to indicate what quadrant you're in, because it's in terms of a variable, you don't know if it's positive or negative. Just draw a triangle and not worry about which quadrant you're in. It's going to be good enough for our purposes today, and I don't want to distract from the lesson today. So make the second example easy and straightforward. Don't worry about 2 possible answers and blah, blah, blah. So try those, and yeah, I'll give you like 5 minutes, and then we'll come back together. So you can see that. So there's a solution for the first one. And one little thing I want to, this is a minor thing, not totally related. But don't forget with the negative, oh, did I screw up? I'm seeing hands up. I must have screwed up somewhere. Trey, where did I screw up? You think it was what? Sorry? Oh, I just wrote the problem down wrong. Oh, man. Okay, well, let's fix that. Woo! Okay, so yeah, the range of arc cosine is different from the range of arc sine, so unfortunately all this work is bad. I got to draw it in a different quadrant. I know, dang it. Okay, let's delete. All right. Does anybody have the final answer that they want to share? What'd you get, Joshua? So it's close-ish. Yeah, and then if we rationalize it, and definitely on the test, you can ask me if you need to rationalize your answers. I'll try to put it in there when you need to. In general, though, if it's just numbers like this, we rationalize, but it's like one of those things where, I don't know. Anyway. All right, let's do this really quickly together then. Which quadrant should I draw my triangle in? 4, yes. Arcsine has almost the same range as arctangent. It just includes the endpoints. And sine is negative in quadrant 4. Always draw my angle by the origin. And draw your triangle to the x-axis always. And then sine is opposite over hypotenuse. Remember, the hypotenuse can never be negative. So definitely the 5, but it's also along the negative part of the axis. And that would make this side root 11. And it's also on the positive part of the x-axis, so we know it's positive root 11. So if we let theta equal arc sine negative 5/6, then we can say the tangent of arc sine of negative 5/6 is the tangent of theta, which is opposite over adjacent is negative 5 over root 11, which matches the answer that was given. Well done! Except I can't write it. Ah. Okay. Yay! Any questions about that one? Good job showing hair, making a mistake again. All right, you ready for the other one then? Let's see. Hopefully I wrote this one down right. Was that the one I gave you? Gosh darn it. I think I was looking at other ones and then changed my mind. Well, let's change this. What did I give you guys? Let's find out. Cosine arc cotangent. Cosine arc cotangent. That's what I get for trying to be prepared, huh? Anybody have an answer they want to give us before we do it really quickly to see what we got? Subra.
X over square root of x over.
Like that? All right, let's see. So again, arc cotangent x is going to be the angle whose cotangent is x, and this is, we should be a little more careful than this, but I'm just going to draw a random right triangle and label one of the angles as theta, and cotangent is adjacent over opposite. So if the cotangent is x, I can think of it as x over 1. And then when you do the Pythagorean theorem to find the hypotenuse, it will be x squared plus 1 in a square root. So any questions getting the triangle? That's like most of the work right there. So, okay. So then the cosine of arc cotangent x. Oh, let me define. If you're going to put a theta in your problem, you need to define what it is. So theta is arc cotangent x. So it is cosine theta. And cosine is adjacent over hypotenuse, which does look like the answer given. Well done, Subreth. Yay! And then this is one, we typically don't rationalize something like this, because it just makes it so much worse. We'll rationalize it if we have to, if we're going to use it later. But look, that's it. That's all the work. Look at that. That's not much work, right? Nah. Any questions? So we're going to use this to help us with the differentiation of our inverse trig. So let's get to the good stuff. Does anybody still need this, though, before I move on? Okay. So let's look at the differentiation of inverse trig. And we're going to start with arcsine. So we're supposed to find the derivative of this. But we don't know how to find the derivative of this. But we do know how to find the derivative of sine. So let's rewrite this. Marcus? Yeah. So what do I have to do first? Exactly. I'm going to rewrite this so it's a sign problem, and then we know how to deal with sign. So if y is equal to arc sine x, then we know that x is equal to sine of y. And then we can take the derivative of both sides using implicit differentiation. So I'm going to write this on the side so that we see it for our notes. Use implicit differentiation. Ugh. So what's the derivative of x? And what's the derivative of the sine of y with respect to x? Yes. Cosine y times the derivative of y. And then we can solve for dy dx. Dy dx is quite simply 1 over cosine y, or you could look at it as secant y. It doesn't matter. Well, there you go. There's a derivative. Yeah, except that's in terms of y. We really need the answer in terms of x. If only we had a way to do this. Yeah. We're going to draw our triangles like we were doing before. So let me just stop here for a moment and make sure everybody's okay with this point. Any questions here? X. Oh, this line right here, right? So all we're doing is we're using the fact that sine and arcsine are inverses of each other. And when you do inverse operations, you also switch x and y. Does that make sense? Yeah. Any other questions? All right. So we're going to go back to what we were doing before now. If we let theta equal the angle whose sine is x, theta equal arcsine x, and then just draw a triangle. And actually, wait a minute, my bad. I don't want theta, I want y. We need this. I'm just using this line right here. So I'm going to draw a triangle. Any old right triangle, and label one of the angles as y. And y is the angle whose sine is x. So y is the angle whose opposite over hypotenuse is x over 1. And then through the magic of the Pythagorean theorem, we can get the adjacent side, which will be the square root of 1 minus x squared. So I'm going to stop there and make sure everybody's okay with that. Yes. So don't worry about it. Yeah, with the variables, we don't know. So that's why I'm just drawing a triangle. Yeah. It's a good question. So any other questions on that? Because then we have our answer. If dy dx is 1 over cosine y, remember, would be adjacent over hypotenuse. So 1 over that is hypotenuse over adjacent. And I can just write my answer. Dy dx is the hypotenuse, which is 1, over the adjacent, which is 1 minus x squared. Ta-da! And now we actually have it. So it seems kind of crazy, but the derivative of arcsine x is 1 over the square root of 1 minus x squared. That will be another one of these formulas you got to memorize. Sorry. So any questions about that? Yes, Charlie. No, because you want to do the hypotenuse minus. Actually, I don't want that. Let me write it out. So if we do our a squared plus b squared equals c squared, excuse me, so we had the x, you see it now? I might as well finish it while I got it. Yeah, b squared is. And any other questions? Okay, so we're going to quickly do this next one together, but then I got two that I'm going to have you guys try on your own. Let's just do cosine x. And we're going to do it pretty much the same exact way. So if you guys want to try it on your own, I'll do it here. I won't talk. It'll be one of those where I do it, but I won't talk, but I won't pause the screen. So, but try it on your own and you can peek up here. So here's the answer here. Any questions about that? One thing I want you to notice, I'm just going to pull the screen down a little bit. You can see the answer we got for arc sine on the top of the screen. And then there's the answer we got for arc cosine. Notice they're exactly the same thing, except for the negative. And you're going to actually find that with all of these. So we're going to find the answer to arc tangent. And then the answer to arc cotangent is going to be exactly the same, just with a negative. And then we're going to find the answer for arc secant. And the answer for arc cosecant is exactly the same, it's just the negative. So the next two that I want you guys to try are going to be finding the derivative of arc secant and arc tangent. Does anybody still need this right now? Because I'll scroll up then just to remind you. So these are the two that I want you to do then. Arc tangent and arc secant. And I'll give you you may not. So here's the answer for arctan if you want to check your work there. But keep going on for. All right, let's look at arcsecant. So arcsecant, pretty straightforward, except you may notice there's an absolute value in there. So ignoring the absolute value, I'll talk about that in a moment. Any questions on everything else? Yes? It is, yeah. I just noticed that too as you were saying that. That is a big bad. Big bird! Whoop. What color did I use? I think I used this one. Whoop. All right, now, any other questions? So let's talk about that absolute value. There's a couple of things with the absolute value, why we need it in there. And again, I'm not going to spend a whole lot of time going into it just because I don't want to take a whole lot of class time. But in the triangle, one way to think about why we need the absolute value. In the triangle, x represents the hypotenuse. I know hypotenuse has to always be positive. So to force it always positive, we put the absolute value. The other thing, if we were to look at a graph of arc secant, the graph of arc secant is actually always increasing. There's an asymptote in the middle, but on either side of the asymptote it's increasing. And so we have to make the slope always positive. And derivative represents the slope, so we have the absolute value there that will force the slope to always be positive. So that's another reason, the way you can look at it. You can also look at using identities to get the absolute value. So just know arc secant and then therefore arc cosecant, their derivatives are going to have an absolute value in them. Any questions on that? So then, let us look at the formulas you need to memorize from this section. So we've derived them, but now let's look at them. I see people writing down those, so I'm going to hold on 1 second. And we will have a cloud. The good news is, actually applying the derivatives, just remember chain rule, it's not that bad. Good old chain rule. Anybody still need this? All right. So here they are. I'm just going to do a quick check. Since I had the mistake up above. Yeah, everything's correct there. So there they are. There are the problems. Or the derivatives to know. And like I said, if you look at the derivatives on the left versus the ones on the right, all the cofunctions are the same thing as their counterparts, just negative. I'll pause the video while you guys. So yeah, take a few minutes once you finish. Try these 3 problems. They're really pretty straightforward. Just don't forget chain rule. And the answers are going to look wacky because the derivatives look wacky. But there's nothing else crazy about these except the formulas. So give them a go. We'll go over them in a moment. So here's the solution to number 2. And I'm going to see if I can fit both 1 and 2. And I'll put up. The last problem was the derivative of arctan of root x. So in case you're like, what was the third one? I don't know what it is. There it is. So example 3. Find the derivative of that. Ooh, let me put up the answer to number 3. And there it is. Bum-ba-dum. I'll go ahead and stop the recording now because that really is the end.